All right, guys, so today we're talking about, well, a lot of things. We're talking about the mean value theorem of integrals, we're talking about average value, and we're talking about the second fundamental theorem of calculus. And all of it is a little bit abstract. I'm going to go kind of slow. This video is probably going to be a little bit longer than normal, but there's a lot of big concepts that we need to cover today. So the first one, the mean value theorem for integrals. Basically what it's saying is if you're taking the integral of a function, so if I'm integrating this function from a to b, let's look at this example underneath it. If I'm going from 0 to 2 of f of x, if I'm integrating, I'm finding the area of that shaded region, right? So if I look right here, if I make a rectangle that's the same width but lower than the lowest value, then obviously my area is less than the real area. Now, if I make another rectangle, but make it higher than the curve, then obviously my area is bigger than it should be. It's bigger than the actual area. What the mean value theorem is saying is that there's some height that we can make this rectangle so that the rectangle's area is equal to the actual area under the curve. So it's saying if you have this weird shaped curve somewhere, you can make a rectangle that's some height that the area of that rectangle will match the area under the curve. Now, what's really powerful about that itself, well, it's kind of a no-duh. You can make a great big rectangle outside of any shape, and it's going to be bigger than the real shape. And you can make a small rectangle and say it's smaller. But what makes it powerful is down here at the end, okay? So what we're saying, and I'm skipping down here a little bit. So what we're saying is from a to b, f of x dx is equal to some y value, some rectangle. I'm taking some y value, and I'm taking the width of my integral, and I'm finding the area of that rectangle, right? So f of c, right here I am solving for f of c to get the value by itself. So f of c is equal to the integral from a to b of f of x dx divided by the width of that rectangle. So I'm just playing with the algebra a little bit. But what this is called our average value. And this one, I promise you, is going to be on the AP test. This is a formula that you are going to have to memorize. This is one that you're going to have down and be comfortable with. What we're saying, the average value of a function is just the average height of the function, pretty much. And so we're saying that f of c, the average value, is equal to the width of the integral underneath the actual integral itself. We're just taking the integral and we're dividing it by its width. It's kind of like taking all, you've added up all of your test scores. Now you're dividing by how many test scores to get the average. That's all we're doing here. So to put this into practice, you're going to see questions like this one. Find the average value from 1 to 5 of this function. So it gives me a function, f of x equals 3x squared minus 2x, and it wants me to find the average value from 1 to 5. Well, the average value, that f of c, is going to equal, remember, it's 1 over b minus a times the integral from a to b of my f of x dx. So when I plug this in, f of c is going to equal 1 over b minus a. Well, here's my b and here's my a. So that's 5 minus 1 multiplied by the integral from 1 to 5 of 3x squared minus 2x dx. So 1/4 my integral, let's go ahead and take the integral of this part right here. 3x squared, that's going to become, actually, I'm going to put my 1/4 on the outside. Here's the hard part of some of these questions. When you start integrating these definite integrals, there's a lot of algebra to keep track of. And sometimes the parentheses and the brackets can get confusing, but just do the best that you can to keep track of what's being multiplied where. This 1/4 is out in front, and I'm going to multiply it by everything else at the end. So I'm just going to leave that 1/4 out in front. Now I'm going to integrate the inside. So this becomes x cubed. I already have a 3, but I need to multiply by the 1/3 because of that x cubed. And then minus, that becomes an x squared. I already have a 2, but I've got to multiply by 1/2 because of that power 2 up there. And again, I'm doing a definite integral, so I don't have to worry about my c. But this integral is going to go from 1 to 5. So here's where it gets a little bit messy, right? Because I've got to plug in, well, let's clean it up a little bit first. So that's 1/4 bracket, 1/3 times 3 goes away, so that's just x cubed. 1/2 times 2 goes away, so that's just x squared. But I'm still evaluating from 1 to 5. So I've got 1/4, I'm going to move over here, multiplied by, now I'm going to plug the 5 in, so x cubed, that's 125, minus x squared, that's 25. But then I have to minus plugging in the 1. See, and I do this every time. I don't give myself enough room. Let's rewrite that over here. 1/4 times 125 minus 25. But then I've got a minus plugging in the 1. So I'm going to minus 1 cubed is 1, minus 1 squared is also 1. So that's 1/4 times 125 minus 25 is 100. And 1 minus 1 is 0. So I'm just left with 1/4 of 100, which is 25. So 25 is my average value. What that means is whatever my function is, whatever it looks like from 1 to 5, if I make a rectangle that is 25 tall, this rectangle is going to have the same area as the curve. And that right there, that 25 is my f of c. That's my average height, my average value of the function. Okay? So given the function f of x equals sine x from 0 to pi, find the average value of f of x, and then find what that c value is that guarantees it. Okay, so same idea. I'm using my 1 over b minus a times the integral of a to b of f of x dx, right? That same function that we've got right here. That's my f of c. So b minus a, so f of c equals 1 over b is pi, a is 0, times the integral from 0 to pi of f of x dx. Whoops, erased my integral. F of x is sine of x dx. All right, so this 1 over pi, I'm going to move out front. And then I've got to take the integral of sine of x. So to get sine, I have to go backwards to cosine, but it's a positive sign, so I've got to go backwards to negative cosine of x. I'm going to evaluate that from 0 to pi. So I've still got 1 over pi multiplied by negative cosine of pi minus negative cosine of 0. See, there's a lot of signs to keep track of here. So 1 over pi, negative cosine at pi. So if I'm looking at pi on the graph, if I'm looking at my unit circle, my cosine at pi is -1. So that becomes a -1. minus negative cosine at 0 is positive 1. So that becomes negative 1. So this is 1 over pi times positive 1 plus 1, which just becomes 2 over pi, not 2 pi. That's my f of c. That's my average height of my function. That's my average value. So now it wants me to find what that c value is. So I know that f of c is equal to 2 over pi. I don't know what the c is though. So if I change my f of c, my function is just sine of x. So that's just saying that sine of c is equal to 2 over pi. Now, we haven't done this yet this year. I don't think we've done inverse sine. A lot of you are going to be tempted to just say, oh, I've got to figure out what that c value is. So I'm just going to do second inverse sine of 2 divided by pi, which is not a terrible idea. Okay, it's not an awful idea. The problem is when you do inverse sine, it restricts your domain. And let me show you what I mean. When I did inverse sine, it tells me that one of the places that this can happen is 0.69. But that doesn't mean it's the only place that it can happen. It restricts the values that it considers. So what I'm going to do instead, I'm going to go up here to y equals, and my function is 2 over pi, right? Or that's my value that I'm interested in. My function is sine of x. So I want to know when my sine of x is equal to 2 over pi, right? So when I graph this, let's get rid of that integral. When I graph this, and I love that I can do this on the calculator, notice that there's multiple places that these intersect. There's multiple c values. All of these intersections right here, these are all c values that make 2 over pi. So I'm going to go to my window, and first thing I'm going to do is restrict my domain. I'm only going from 0. So my x value is going to be 0. My maximum is going to be pi. And that's going to help because now I've only got 2 intersections right here. Okay, I've got 2 values that give me 2 over pi. So when I did it on my regular calculator, I had 1. When I look back here, the 0.69, that's one of my values right there. But there's another one. So I'm going to go ahead and just use my intersection, second calculate, intersect 5. And I just need to get close to this one, and I'm going to hit enter, enter, enter. So one of them, when x is 2.48770. So let's go back here. So when c is 2.48770 or something like that, right? 2.48770. Okay, my other intersection, second calculate intersection, I've got to come all the way over here, and I'm going to hit enter, 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 and that's my 0.6944, right? 0.6944. Which is what my calculator gave me back here, my 0.69. Are we in radians? We are in radians. Okay. 0.6901. Why are we... I guess we're just rounding off a little bit, aren't we? Okay, so be really careful with your inverse functions. It doesn't give you all the possible answers, okay? So there are 2 values of c that give us that result. But if I use inverse sine, I'm only going to find one of those values. So be careful there. All right, moving on. Let's do an AP question. So This question it's number 6. It's from the 2003 test. Now, one thing to be careful of about this question is I know that this is a no calculator question. Numbers 1 and 2 on the free response let you use the calculator. Number 3s through 6 are no calculator questions. So I know that I'm not going to be able to use my calculator, or I'm not supposed to use my calculator on question number 6. So we're going to try and do this one without a calculator. And it gives me a function, a piecewise function. It wants me to find the average value from 0 to 5. The average value from 0 to 5. Okay, so I know average value, and I'm going to do my work underneath the box here a little bit. I know that average value equals 1 over b minus a, integral a to b of f of x dx. So my average value is going to equal my integral. I go from 0 to 5, so 1 over 5 minus 0, from 0 to 5 of f of x dx. Now here's where things get interesting because I have a piecewise function. So my f of c equals 1/5. I'm going to break up this 0 to 5 because when I go from 0 to 3, my function is square root x plus 1. And we're going to use x. I know they're not using x, but we're going to use x because why wouldn't we? Or maybe that isn't x and it's just printed really funny. I can't tell. But I can just add that to the integral from 3 to 5, but I have to use the 5 minus x dx. We should probably put the dx's there so we don't get into trouble. All right, now we get to do some fun integration. For this one right here, I'm going to set u equal to x plus 1. So that means that du is equal to 1 dx. So that's nice. When I plug in, let's see, how do we want to break this up? So that just becomes, oh, actually, you know what? From 0 to 3, I can plug those values in to my u and change my integral. So f of c is going to equal 1/5 times, I'm going to integrate, when I plug in a 0, 0 plus 1 becomes 1. When I plug in a 3, 3 plus 1 becomes 4. So I'm actually going from 1 to 4 of the square root of u du, plus this one I can still go from 3 to 5 of 5 minus x dx. I can handle that one just fine. So plugging in this first part, 1/5, 1 to 4, remember that this is just u to the 1/2. So I'm going to get 1/2 u to the 3/2. Nope, 2/3. What am I doing? 2/3 u to the 3/2. Because we've got to add 1, so that makes this 3/2. So I times by 3/2. But then I've got to integrate that. I've got to do that from, what are we, 1 to 2. And then I'm going to add this 1/5. I'm going to go ahead and distribute this 1/5 right here to this integral and to this integral. So 1/5, the integral of 5 minus x, that becomes an x. Come on, pencil. That becomes an x squared, but it was a minus. So I've got minus 1/2 x squared. And that 5 becomes a 5x. And I'm evaluating that from 3 to 5. I told you, lots of algebra. So 1/5 multiplied by, well, maybe we didn't want to distribute that 1/5. Maybe we wanted to leave it out in front of a bigger bracket. So 1/5 multiplied by 2/3 times 2 to the 3/2 plus 2/3 times 1 to the 3/2. Nope, not plus, minus 2/3 plus, I'm going to plug in the 5. So 5 times 5 is 25 minus 1/2 x, nope, not x, because I'm plugging in now. Come on, pen. You change to erase when I don't want you to. 1/2 5 squared minus, now I plug in the 3, 15 minus 1/2 3 squared and that looks like a big ugly mess. So I'm just going to clean it up just a little bit. Not a lot, because this is a free response question. So in fact, if I just put this there, that could be my final answer. I could be done with that one. If I wanted to clean it up a little bit, I could leave the 1/5 out front. 2/3 times 2 to the 3/2 just becomes 2/3 times the square root of 8 minus 1. Nope, minus 2/3, because 2/3 times 1. And then I get the plus 25. I get minus 25 over 2. And then I get minus 15. And then I get plus 9/2. Again, a whole bunch of messy algebra. I would have left it right here. Okay. In fact, if you look at the answer key, and the answer key is buried underneath this box, which I can't move. But the answer key that's buried underneath there says that you get 1 point for splitting the integral. So right here, where did we split our integral? Right here, you would have gotten a point for that part right there. You get 1 point for finding the integral of square root of x plus 1. You get 1 point for finding the integral of 5 minus x. And you get 1 point for the answer. So we would have gotten a point for this part if it was correct, a point for this part if it was correct. And then when we would have had a point for the big thing. As long as we're doing it correct, of course. They're not going to give you a point for the wrong answer, but as long as you're doing the work correct, you would have gotten a point for that one too. Okay? All right. Jumping into a new idea. Our second big, or third, I guess, big topic here is our second fundamental theorem of calculus. Now, this one says, basically it's saying that the derivative of the integral is the original function. Okay, if I take the derivative of an integral, I get the original function. But it's not, I have an issue with presenting it just this way, because it doesn't give you the full picture. It gives you a specific example. And that example is when our bottom integral, our bottom bound is a constant and our top is an x. Okay? So when the bottom is a constant and the top is an x, this is absolutely true. That the derivative of the integral is just f of x. But here's what I need you to know. Is the derivative of an integral, it's actually f of x multiplied by, and here's where we've got to be a little bit careful. It's multiplied by the derivative of the top bound. And the best way that I can write that right here is the derivative of whatever's on top. And then you have to minus f of the lower bound, f of a, times the derivative of that lower bound. Now, when I do that, when I take f of x times the derivative of x, well, the derivative of x is just 1. And when I take the derivative of a, I get 0. So for this example, my answer comes out to just be f of x. But it's not always f of x. Because of this chain rule, it's only f of x when you're going from a constant to x. So this first example right here, I'm going from 0 to x, which means my answer is just x cubed plus 2. That's my entire answer because I'm going from 0 to x. But in this second example, I'm going from 3x to x squared. So the way that I do that is I'm going to take f of x, so f of the top, which means I've got to plug that in. So I take the square root of x squared cubed plus 2, but then I have to multiply it by the derivative of that upper bound, which is 2x. That's my chain rule right there. And then I plug in the bottom, the square root of 3x cubed plus 2, but I also have to times that by the derivative of the bottom bound, 3. So my answer becomes this 2x I'm going to move out front, 2x root x to the 6th plus 2 minus, what is that? Square root, actually let's put that 3 in front as well. Let's move this 3 out front, square root. 3 cubed is 27, x cubed plus 2. So that would be my answer. And I have an issue with it being presented just this way because it minimizes when you can use this theorem. This is actually a really, really powerful theorem, not because the derivative of the integral is itself, but because all you have to do is multiply by the derivatives of your bounds, and you can take that integral really easy, okay? So let's try a couple more. The functions f and g are given by f of x from 0 to 3x of 4 plus t squared dt, and g of x is equal to f of sine of x. Find f prime of x and g prime of x. So f of x is this right here. So it wants me to take the derivative of an integral. So it's asking me, take the derivative of the integral 0 to 3x root 4 plus t squared dt. Well, that theorem that we just learned tells us I'm going from a constant to 3x. So my derivative of that integral is just the integral, or just my function, 4 plus, and then I've got to put 3x squared. But don't forget that we have to multiply by the derivative of the top. And the bottom, I don't have to worry about doing the bottom bound because it's a constant. It's just gonna multiply by the derivative of 0, which is just 0. So it's gonna go away. So f prime of x is just equal to the square root. Actually, let's move that 3 out front. So 3 square root 4 plus 9x squared. So there's my first part. F prime of x equals 3 root 4 plus 9x squared. Okay? And again, if you're just looking at the second fundamental theorem of calculus, you might stop right here and forget to times by that, the derivative of that bound. We've got to be careful. The chain rule is going to affect the math on this one. So part 2 wants me to find g prime of x. So g prime of x equals, well, it equals the derivative of g, which is f sine of x, right? G prime is the derivative of f sine of x. Well, the derivative of f sine of x, well, the derivative of f is f prime of sine of x. But chain rule tells me that I've got to multiply by the derivative of the inside, which is cosine of x. So f prime of sine of x, cosine of x. Well, I know what f prime is. I found it right here. So that means f prime of sine of x. So 3 root 4 plus 9 sine squared x, all multiplied by cosine of x. And because this is free response, I can stop right there. I don't have to. I mean, I could say g prime of x equals 3 cosine x root 4 plus 9 sine squared of x. Either one is the correct answer. And it's not going to, I'm going to give you credit either way as well. So, all right. I know the video is running long, but I want to do 2 of these on the video really quick, and then we'll do 2 of them in class. So we're going to do this one in class and this one in class. We'll do those together. But these ones on the left-hand side, let's do those. So the derivative of the integral. So I know I'm going to use the second fundamental theorem because I'm taking a derivative of an integral. And my bottom's a constant, which is awesome because that means all I have to worry about is the top, because the bottom is going to go to 0. So the derivative of my integral just becomes 1 over root x to the 4th to the 3rd plus 2. But then don't forget that you have to multiply by the derivative of that x to the 4th, which is 4x cubed. So let's see, what do I get? I get 4x cubed on top, and on the bottom, I have square root of x to the 12th power plus 2. Which looks good to me. When that bottom's a constant, these are really easy. The second one, my bottom is not a constant. My bottom is 3t, and the top is, what does that say? T to the 5th, I think. Nope, t to the 3rd. All right, so we have a couple of options here. I know that 3t is smaller than t cubed because it's on the bottom of my integral, right? So I can assume that that's the smaller number. And I think we can, I guess we have a couple of different options here, all right? So one of them is to just do what we've been doing. I take my bottom's not a constant, so it's not going to go away, so I can't just ignore it. So we've got to start with the top. So I just plug this in. So my derivative of my integral is going to be t cubed plus 1 to the 10th power. Holy smokes. But then I have to multiply that by the derivative of the top, which is 3t squared. And then I'm going to minus the derivative, or the bottom I'm going to plug in. So 3t cubed plus 1 to the 10th multiplied by 3. So if I clean this up a little bit, I get t to the 9th plus 1 to the 10th power. That 3t squared I'm going to go ahead and put in front. And then I'm going to minus 3 times 3t cubed becomes 27t cubed plus 1 to the 10th power. And I'm not going to worry about cleaning that up at all. I'm okay with that being the way that it is. You could, I mean, there's things that you could do. You could factor out a 3, but that's not going to make it look any better. That's just going to make it look messier. You are more than welcome to take stuff to the 10th power, but no way. That's going to be a great big ugly. No, we don't want to do that. We're going to leave it just like it is, okay? So the other thing that we can consider on this, and this is maybe something that we'll look at in class, is breaking up those integrals. And in this case, it may or may not help, but we'll try that on this second one in class when we do that together. So I know this was a lot in one video. It's going to take a little while to wrap our heads around it. Practice lots of problems. We'll go through those together in class next time I see you.